I like the blurry when it refocuses the camera because that's like a simulation of you looking at the paper. Because you're like, oh, and then like you'll like wake up again. And it should just do that randomly, simulate the student perspective. It's like a first person view of what's going on in a math class. You're like taking notes and then it like blurs, lets you go to sleep. And then it gets back and then you start writing again. Anyway. Today we want to go back to limits. We've had some review in the homework on some algebraic stuff. So let's see how we can use that in calculating limits. We also needed to wait to do this part until we got continuity. So remember that a function is continuous at x equals c if and only if the limit as x approaches c of f of x is equal to f of c. What this means is that for a continuous function, we can evaluate a limit by just plugging in the point. That's what we want to observe now. So if a function is continuous at a point, we can evaluate limits by plugging in. That's our takeaway from this. For a continuous function, if a function is continuous at a point, we can evaluate the limit of the function at the point just by plugging in the numbers. Now, this raises the obvious concern. It's like, oh, dude, we are always worried about the limit at points where the function is doing something weird and we can't just plug in. And that's where algebra comes into play. So for example, an example of what I mean for evaluating limits by plugging in, if I wanted to find the limit as x goes to 3 of x squared is continuous at 3. As x goes to 3, we'll be headed towards the value of the function at 3. We can get away with just plugging in. Easy. That's why we like continuous functions. And there are a lot of better reasons to like continuous functions. This is one of them. So how can we use this continuity business to our advantage? The idea that we're going to use is we're going to get rid of the things that make the function undefined. Sometimes we can get rid of factors that make the function undefined. And we have done this before. This is just a repeat with more details. We're going to use algebra to get rid of whatever is making our function discontinuous. This is a very hand-wavy way of saying what we want to be doing. So we're going to use algebra to get rid of whatever is making our function discontinuous. Once we do that, then we can just plug in to evaluate the limits. Once we get rid of whatever factor is making our function discontinuous, then we can just plug in to evaluate the limits. We have done this before. So for example, if I want the limit as x approaches 2 of x squared minus 4 over x minus 2. The reason that we can't plug in is that plugging in 2 gives us a 0 denominator. Plugging in 2 is giving us a 0 denominator. It's also giving us a 0 numerator, which is why we know that this is going to work. The problem factor is the x minus 2 in the denominator, and that's what we want to try to cancel out. So what we observe is this x minus 2 in the denominator is why we can't plug in. We can't plug in because the x minus 2 factor in the denominator. What we want to notice is that if I try to plug in 0, we get, or sorry, try to plug in 2, we get 0 over 0. 0 over 0 gives us hope. Constant over 0, always going to be a problem. Nothing we can do about it. So moreover, we get 0 over 0 if we try to plug in. That's what's giving us hope. So, oh, this is going to give us a 0 over 0. 0 over 0 suggests that there's a possibility of just a break. So what we're going to do is we're going to use algebra to cancel out the x minus 2. I'm going to factor out the numerator. This is why we can see the 0 over 0. That's telling us that there is a common factor in the numerator and the denominator in this rational function stuff. So we can actually get rid of what's causing the problem. X minus 2 is the problem. We can get rid of that. What's left over is a function that is continuous at 2. This is not equal to the original expression. X plus 2 is not equal to x squared minus 4 over x minus 2. But the only place it's not equal is 2. And we don't care what's happening at 2. We care about what's happening near 2. But we've taken care of the problem, so now we can plug in. This is algebraic workarounds. 2 plus 2 is 4. So x plus 2 is not equivalent to the original expression. It's only equal when x is not 2. They aren't always the same, but the only place they're not the same is the point that we don't care about. So we want to note that x squared minus 4 over x minus 2 only equals x plus 2 when x is not 2. On the left, it's undefined or indeterminate. On the right, it's 4. But we don't care what's happening at 2. We care what's happening near 2. This is one strategy. Try to get rid of the bad value. To get used to this, we come up with all kinds of contrived examples that do weird things. Oops. I spelled 6 wrong. When we try to plug in the 2, oops. We get 0 over 2 squared is 4 plus 2 is 6 minus 6 is 0. We get 0 over 0. So this tells us that we're going to be able to cancel out an x minus 2. We're just reading and taking what we know about rational functions. We know that we're going to be able to cancel out an x minus 2. I mean, that's exactly how I built this function in the first place. But that's how we would observe that. 0 over 0 at the value we're trying to find the limit means we're going to be able to get rid of it. So this will be the limit as x approaches 2. I'll factor the denominator. So we've gotten rid of the value that's causing the problem, or the factor that's causing the problem. So we get 1 over 2 plus 3, or 1/5. The function was discontinuous at 2, but it was just a hole in the function. We know that this is going to work because we can see that we're going to get 0 over 0. This happens on this one, and it happens on that one. That 0 over 0 in a rational function means there's a common factor in the numerator and denominator we need to get rid of. We got to be careful how we summarize things. We can't just say, oh, if we can cancel a factor, then we just need to plug in. So we have to make sure that we're... The other thing that could go wrong with this would be as x approaches -3, that's also going to be a problem for this function. In this case, as x approaches -3, we still get a 0 denominator. -3 squared is 9, 9 minus 3 is 6, 6 minus 6 is 0. 3 gives a 0 denominator, but it doesn't give a 0 numerator. The -3 gives us -5 over 0. That's no help. That means it's not going to work. So we notice if we try to plug in 3 or -3, we get -5 over 0. We're not going to be able to cancel out anything that matters. We won't be able to cancel out anything that helps. If we try it, we can cancel out the x minus 2, but that doesn't help us in this scenario because we care about what's going on at -3. I didn't square it, so it's just positive or negative infinity. So this limit does not exist. We're able to cancel out the x minus 2, but the x minus 3 is sticking around. When we look at the original function, we have two values of x that are not in the domain. One of them was a hole in the graph. The other one was a vertical asymptote. Vertical asymptote we can't fix by canceling. Hole in the graph is there because we can fix it by canceling. So when we look at because the x minus 2 cancels out, that tells us there's going to be a hole in the graph at 2. But since the x minus 3 doesn't cancel out, we have a vertical asymptote. At x equals -3. How's everybody okay? I bring this up maybe so mainly so I can bring up rational functions and our understanding of rational functions. Give a little reminder of how the undefined points in rational functions show up. Also, we want to reinforce the idea that one of the things that we want to be able to do is cancel out whatever factor is causing us to not be able to just plug stuff in. We want to know that this is an okay thing to do because it works algebraically. And we want to reinforce that it's okay to do algebraically because even though these two expressions are not equal everywhere, they're only unequal at a point we're not interested about what's going on because we're looking at a limit, not evaluating a function, even though we're trying to evaluate a limit by evaluating a function. How's everybody okay? We're just trying to get to the point where it's like, oh, when can we just say, let's just plug it in, simplify it, and then plug it in. We want to get to the point where we can say stuff like, when is 0 divided by 0 equal to 1? When is 0 divided by 0 equal to 0? When is 0 divided by 0 equal to 5? On one hand, we really like it when we get to customize our stuff. On the other hand, it's really kind of a pain because now we have to customize our stuff. Computers are especially bad at this. You start using some app, it works a certain way. The developers come up with some clever new way that will be way more efficient, except the fact that it's efficient for them. And now you have to adjust the habits that you've built over the last year of using the app. I'm looking at you, Microsoft. Yes, I'm continually mad at Microsoft. I suppose I could just stop using Microsoft, but I've just indicated that the problem I have is that you keep changing it, which indicates that I have a problem with changing things. So it makes you think I'm going to jump ship. I still think about that. And Microsoft's like, oh, you're not going to leave. It's like an abusive partner. You're not going to leave. You need me. Oh, I need Microsoft, man. Anyway. How's everybody okay? I should take the opportunity to make fun of Bill Gates. So I don't know if I have the energy to do it, but just know that I make fun of Bill Gates too. My favorite was when they had this small schools initiative. Like they observe, oh, look, all these small schools are high performing. And these large schools, more better performing than these large schools. But then you look at a graph of the small schools that are high, I'm going to do your perspective. The small schools that are high performing, these larger schools are lower performing, but you would know what else was even lower performing than that? Some more small schools. It's almost like the big schools had more contributing to the average. The big school is going to, the bigger the school, the more the student body will tend towards the average. You pick the right small schools, they'll be on the higher end of things. You pick the wrong small schools, they'll be on the other end of things. Because unsurprisingly, it's not the size of the school. On to Bill Gates' credit, he has said, well, yeah, we were wrong on that one. But this is why we don't just want to let the billionaires try to run everything with whatever crazy fucking idea they come up with. So go, this is how it should work because I said so and I'm the one with the money. Bah! It's like, oh yeah, but if we take that money from you, then we can collectively decide what to do and work better for the average rather than just one dude. No, but I want to spend money on what I want to. I earned it. Earned it. What are we talking about? Oh yeah. How did you develop these views growing up in the 80s in the United States? I don't even know. All right. This example is super contrived, but we have not always seen this. So I want us to have seen this at least once in your calculus career at this point, or in your mathematical career at this point. Notice I've written the square root of x minus 2 over x minus 4. The reason that I want to do this is that we don't always, when we think about factoring polynomials, we always think about factoring over integers, and we also think about factoring into other just more polynomials. So we can't factor a degree 1 polynomial because 1 is the smallest integer, and that's what we use on polynomials. So that's why I automatically throw in this square root of x minus 2 to suggest that we're not dealing with rational functions here. We're dealing with what we can do algebraically. And this is not a kind of factoring that we will normally do. Notice if I plug in 4, I get root 4 is 2 minus 2 is 0. And in the denominator, 4 minus 4 is 0. I get 0 over 0 at 4. That tells us there's something to factor and cancel. Not something obvious for us to factor and cancel if we've gone through the standard algebra training. So we can still factor the difference of squares. So note, we get 0 over 0 at x equals 4, suggesting there's something to cancel. This is not a rational function, but I'm thinking in terms of rational functions. We're still doing that thinking. What we're going to do is factor the denominator. Zero over 0 at x equals 4 suggests there's something to cancel. So we're going to apply the difference of squares, even though it's just an x minus 4. X is the square root of x squared. 4 is 2 squared. I'm using the difference of squares. No one usually calls me on the fact that the square root of x squared should be the absolute value of x. And so I'm going to gloss over that right now. That's called steamrolling. But we want to see what happens is that when we cancel the thing out, we get 1 over the square root of x plus 2. And now we can plug in the 4. Square root of 4 is 2 plus 2 is 4. We get a 4. We're reading it like a rational function, even though it's not a rational function. This limit brought a non-rational function to a rational function fight. Any questions? This is going to be our goal if we happen to be called upon to use the definition of the derivative to find the derivative at a point, or even find the derivative function. So the definition of the derivative is a limit as h goes to 0. And the reason that this is sneaky is that the denominator of the expression for the derivative, the expression which is the slope of a secant line, the sneaky thing is that the h appears in the denominator. That's why we can't just plug in 0. It gives us 0 over 0. It's exactly what we've been talking about. We get f of x plus h minus f of x all over h. So the problem is that there's an h in the denominator. That's why we can't plug in. If we try, we get 0 over 0 at x or at h equals 0. So that suggests there's something that we can cancel. We can't just plug in 0 because we get 0 over 0. We don't know what that is. But this suggests if we can eliminate that h, then we can plug in 0. We've seen an example of this. We dealt with x squared. We just multiply stuff out. We cancel the h. Our goal, our thinking is play rational function games. Try to cancel the h, because if we can do that, we can just plug in h. We can let h go to 0. So our thinking is to try to cancel the h. We know this works on polynomials. So first of all, note that we already know the derivative of x squared is 2x. That's not the point. The point is putting our algebra together with the things that we understand about the slope, the derivative being a slope of a secant line that we make look like a tangent line. So we already know f prime of x is equal to 2x because nx to the n minus 1. My 2, though, looks too much like an n. I gotta fix that. But this is math class. It's not about finding the answer. It's about thinking about math. So f prime of x will be the limit as h goes to 0 of f of x plus h, which will be x plus h squared minus f of x all over h. Once again, plugging in h equals 0 gives us 0 over 0. Let's try to cancel that h. And so we're just going to hit this with the algebra stick for a little while. The numerator does give us something to do, so we just do the thing. This is called following your nose. The important thing, what happens here is the x squared and the x squared cancel out. Everything else has an h left over. So what we notice first is that x squared minus x squared we've still got h over h going h in the denominator. We've still got an h in the denominator, but now we can cancel out the h. In the numerator, every term has a factor of h. I don't know what your particular view of in simplifying this expression would be. So I'm going to write down all the gory details. Note that I have to keep writing h go to 0 because h hasn't gone to 0 yet. So if we factor an h out of the numerator, that's when we can cancel the h. That's getting rid of the problem. That's taking care of the problem. And so we got limit as h goes to 0 of 2x plus h. And now when we let h go to 0, when we just plug in h equals 0, we just get the 2x that we expected. Just as we had foreseen. So we get our little emperor moment. It's just as we had foreseen. My version of Return of the Jedi, when Vader grabs the Empire and chucks him down the big safety violation. The Emperor's like going, I saw this coming. So for square root of x, we already know what the derivative looks like because of nx to the n minus 1. Super powerful. Saves us from doing a lot of algebra. Lucky for us, because we don't necessarily always remember all of our algebra. Let's see what happens in this case. Let's do g prime of x is the limit as h goes to 0 of the square roots of x plus h minus the square root of x all over h. Once again, at h equals 0, we get 0 over 0, suggesting that there's something algebraic that we can do to cancel things out. In the previous example with x squared, all we had to do was multiply some stuff out. But here, I've got a square root of x plus h. So there's not really a multiply this out scenario here. So we have to bring in some other trickery. What algebraic maneuver can we use on this function? Secretly, I kind of, oh, go ahead. It is multiplying. What do you want to change? Multiply by a square root. Correct. That's what we want to do. We're gonna do one of our 3 favorite tricks in math. The 3 great tricks of math are add 0, multiply by 1, which is what we're gonna do here, or just shift to an easier problem. Translate down to an easier problem, then translate it back up. We have these radicals. The h is sitting under a radical, so we are going to rationalize the numerator in this case. We're going to rationalize the numerator in this case. And secretly, I already showed you how we're going to do this. That's why I did this example up here. See, that was foreshadowing. That's like at the beginning of on tonight's episode, on previous episodes of Game of Thrones. They show you which characters they're going to be talking about in this episode. I like referencing Game of Thrones because that is like the biggest collective forget that we've ever had. It's like everybody's like, "Oh, Game of Thrones. We all talk about Game of Thrones. If you're not talking about Game of Thrones, then you are out of the loop." And then season 8 happened and it just disappeared. We just stopped. Full stop. No more conversation about it. It's like, oh, no one gave a shit immediately. But anyway, what we're going to do is we're going to multiply by 1. That is a shitty description of what we do, but it's funny that way. We're going to multiply by 1, but we're going to do it in a specific way. We're going to rationalize the numerator. I'm going to get rid of these radicals by multiplying by the conjugate of the numerator. If I do a square root of x plus h plus square root of x, this is actually putting the radicals into the denominator, which is okay, because it's going to pull the radicals out of the numerator, leaving h all alone and ready to get canceled. In the denominator, I still have this h, and we're multiplying by this square root of x plus h plus the square root of x. In the numerator, I've got the square root of x plus h times the square root of x plus h. That's just going to give us an x plus h. It's the difference of squares. So I'm going to have minus, the 2 in the middle will be plus root x plus h, and minus root x plus h. Those cancel out. And I have minus root x times plus root x. So I'm going to have minus an x. Notice that the same thing is happening here. The stuff in the numerator without an h cancels out. So the denominator still looks messed up, but the important part is that that h is hanging out ready to be canceled. So the h's cancel out. And our maneuvers have produced a result that we wanted. Because now we're looking at the limit as h goes to 0 of 1 over square root of x plus h plus another square root of x. And now, when we let h go to 0, I got 1 over the square root of x plus another square root of x. That's 2 square roots of x in the denominator. Just as we had foreseen. So I'm definitely cheating here, saying we can do algebraic maneuvers, and this is what we're going to go for. We're going to use these algebraic maneuvers. This does break down when we start to get to things like sine x, cosine x, e to the x, because those aren't algebraic functions. I know we learn about them in algebra, but those are transcendental functions, not algebraic functions. A similar thing happens if I had a rational function. I talked too slowly to get through the third example where it has 1 over x squared. But when we have 1 over x plus h squared, we're in the same scenario that we were with x squared. We have some algebraic stuff that we can just do. We can just simplify the complex fraction, cancel out the h, plug in h equals 0. Our goal is to cancel out the problem factors. Cancel out the problem factors. Any questions, comments, deep thoughts? Cool. That's going to do it for today. I will see you all. Oh, that's going to do it for this week. I will see y'all on Monday. Everybody have a good weekend, and thanks for playing.